In this problem, we have a circular disk here that has a surface charge density of sigma, and our goal is to find the electric potential at some point P that is on the rim of this circle, so any one of these points here. So I suggest that we choose a point that's on the rim of the cylindrical disk so that we can conveniently place a coordinate axis here, if I can draw on a straight line, a coordinate axis here, and we can place that point P at the origin. So we'll go ahead and put that point P right there. And so, of course, since we're finding the electric potential, one way we can find the electric potential is we can just integrate all these small contributions of the electric potential from every little point on that charged disk. So each and every one of these points is going to have some contribution to the electric potential at that point. And so what we got to do is we just got to integrate all those up, and we have our electric potential. As you may recall, the electric potential is equal to 1 over 4 pi epsilon naught of the total charge Q divided by the distance. So really, we can change this into differential form by taking little chunks of dq that are on the disk, and then finding the distance, the separation vector from them, and integrating over space. And the way that looks is what I'll write here. We'll just turn that into an integral form, equals 1 over 4 pi epsilon naught, an integral dq, let's draw that a little bit neater, dq over r, okay? And of course, as you might have guessed, we can represent our dq in terms of things that we were given, such as the sigma and dA here. All right, so we'll go ahead and make that substitution right there and place that in there. 1 over 4 pi epsilon naught, integrate over sigma dA over r. And also, one thing I forgot to mention, we can turn this dA here, and we can turn that into the surface area for the, something more sphere or cylindrical. So we can use in terms of d theta dr here to make a little infinitesimally small, let me zoom in here, infinitesimally small surface charge. So if we take this here, we call this our d theta. Oh my god, that is not small enough. So we'll call this d theta, right? And then a little surface charge density patch right here. This is equal to, this distance is dr, and this distance right here, that is equal to r d phi, right? So that means our infinitesimally small dA area is actually equal to the product of those, so that'd be r d theta dr. So we'll go ahead and make that substitution right here, r d theta dr. And this is over some limits of integration for the area. As you can see right here, we have two r's conveniently cancel out. So we have now equal to 1 over 4 pi epsilon naught times two limits of integration. I'm going to go ahead and pull out this constant. So this is sigma is actually a constant here. D theta dr. All right, so that's a pretty easy looking integral. The only thing that we have to figure out is what are the limits of integration here. Now, if we zoom back over here to figure out what the limits of integration are, so we have, since we're doing like these polar coordinates where z is equal to 0, right? So it's just a flat disk here. We know that we want to integrate over all the space to capture all these things. So we'll integrate, if we just go ahead and call this angle from this axis here to wherever we are evaluating that infinitesimally small point at, we'll call this theta, right? And so if that's theta, we want to integrate over this whole surface right here, right? So this would be equal to pi over 2 to pi over 2, negative pi over 2, if we're going to go over that range, right? And so we're also, so that makes sense. So that's our limit of integration for theta, right? It goes from pi over 2 to negative pi over 2. Now for r, what about r, huh? We know at the biggest extent, we're going to go all the way out to r is equal to 2r, right? And we were given that the radius of this circle is equal to r right here. So we know that at the most it goes out to this, which is just 2r, the diameter. But as we span out over our d theta right here, dr is going to change, or the value of r is going to change, right? So I guess to make it a little bit more explicit, let me go ahead and change this to orange, right? So when theta is equal to 0, it's going straight up, and there is no value. The r value is equal to 0. But whenever theta goes out to 0 here, or straight out here, we know it goes out all the way to 2r. And then as it spans out, let me switch back. As it spans out, the r value is just going to change, right? It's going to have a certain different value that is in relation to theta. And that has, and the way we can capture the way that r changes in regards to theta, we can use something convenient called Thales theorem. Let me go ahead and actually make some room here. So we know that if we have a point here and a point here, and some point on the rim of the surface, if we make a triangle using all three of those points here, this Thales theorem always says that this is a right angle right here, right? And so if we know that this is 2r and this is our theta right here, this leg right here, this is our r that we're evaluating from. And so we can figure out what that length is using these two values right here. And this is what this is the value that changes, the variable here. And so we know that this side, of course, if we use SOHCAHTOA, cosine of theta is equal to we'll call that r, right? Is equal to r over 2r. So SOHCAHTOA, right? And then we go ahead and solve for r, our variable. R is always going to have the relationship of 2r cosine theta equals to r. And this is what we can use for our limit of integration. It's always going to start from 0, and then it's going to go out to some value and then come back. So at theta equals pi over 2, we want it to be 0, and that's what this works out to be. But when theta equals 0, we want this to be equal to 2r, which is what this will equal to, because that goes to 1. And then when this goes down to 0, or when this goes to negative pi over 2, then this whole value here goes to 0, right? And so that's exactly what we're going to be working towards here. So we'll go ahead and make those substitutions for our limits of integration, change this back to white. So for our d theta, it's going to go from, it doesn't really matter, so we can go pi over 2 to pi. It doesn't really matter the order since we're finding the magnitude of the electric potential. And then this will be 2 cosine, 2r cosine theta. And then we'll go ahead and do our limits of integration. We'll do that outside first since we have to get our theta derivative in there. So that's really the first derivative. Let me go ahead and put this down here. dr. The theta or the r, this is theta. The r integral, these outside ones, is just going to be equal to 2r cosine theta, right? We have 2 r's. I actually just dropped a 4, I'm not sure why. So this cancels out with this, makes that a 2. Reminder, this r can move out in front, so when I drop down to this next one, we can go ahead and call this r sigma 2 pi theta. And then now we just have the integral of cosine d theta evaluated at these integrals. So we know that's just sine theta evaluated from pi over 2 to negative pi over 2, which is pretty easy. That's just equal to 1 minus a negative 1, which is equal to 2. That 2 will cancel out with this 2, and that's left with our final answer, r theta, or r sigma pi over epsilon naught. And that is our value for the electric potential evaluated at that point.